Hello everyone. So in this lecture we are going to discuss about the NOR implementation of any logical circuit. So as we have already discussed in our previous lectures that any logical circuit created using AND OR can be converted into circuits containing NAND or NOR. And if you think about it, NOR is nothing but the dual of NAND. So NAND is the dual of NOR, isn't it? So x, y dash, and this is what x, y dash. So this isn't this not the dual? Similarly, this is also the NOR is also the dual of NAND. So it's so you can use the same rules that we have used for NAND, and we can convert any circuit in the AND OR format into a NOR format. So for the basic operations of AND and OR, the equivalent structures would be, so if my operation is OR, so that is X or Y, I use the OR gate, I get X or Y. So if I have to use a NOR gate for this, I will write it as XY. This is the NOR gate. Okay, and then what we do, just complement it. So here what I get is X or Y complement. So when I complement this, I get X or Y. Similarly for AND, I have X complemented, Y complemented, okay, and then pass it through a NOR gate. So what we get, X complement and Y complement passes through it, so I get X complement or Y complement, so which is nothing but XY. So these are the equivalent structures for OR. So this is for OR and this is for AND, using only NOR gates. And again, just like we have two graphical symbols, for NAND we have two graphical symbols. So the graphical symbols used, that are used, I can write like this. So XY. So this format is known as a OR invert. OR invert. Or I can write it like this, XY. This is known as a invert AND. Invert AND. Important to remember, both of these are your NOR gates. So you can represent using any of the two notations. So let's take an example. So I have F is equal to A plus B into C plus D into E. So I will not draw the representation using simple AND and OR gates so that you can do it very easily. So let us look at the implementation using NOR gates. So for every input A, B, okay, A and B, we use a NOR gate here. So what do I get here? A plus B complement. Similarly, C and D, use a NOR gate here. I get C plus D complement. And E, because it's a single literal, we will pass it through a inverter. Okay, so I get E dash out here. And then again, now here we can use a we can use either this format, that is a invert AND. Okay, so the input which is coming from here, which is this is converted, is again negated and then sent here. So what I will get out here is from here I will get A plus B, then from here I will get C plus D, and from here I will get, from here E dash goes in, so what comes out is E, and this here is a AND, so I can write it as A plus B into C plus D into E. So this is one representation. Or I can use all of the NOR gates, and I can write it as AB. So use a NOR gate out here, so I get A or B dash, then I get C or D dash, then I send in E as complement. Okay, and I use a OR invert, so I pass E dash out here. So what do I get here? F would be equal to A plus B complement plus C plus D complement plus E complement, whole thing complement. So if we expand it, I will get A plus B complement, this plus will become dot, then I will get C plus D complement, again this plus becomes a dot, and E dash complement. So this, when we expand, we get A plus B dot C plus D dot E. So this is our F. So what we have done is we have converted the circuit into a circuit containing only NOR gates. So this is how you can do the transformation.